Thank you all for coming. I'm happy to be here to introduce our work about efficient image vectorization with adaptive parameterization. In recent years, we have witnessed significant progress in image vectorization, particularly with the adoption of optimization-based and neural network-driven methods. These approaches have demonstrated improved vectorization accuracy and the ability to handle relatively complex images. However, a fundamental limitation remains. Existing methods typically rely on a fixed number of paths and control points, regardless of the image content. This rigidity doesn't really account for how different parts of an image can vary in complexity. It ends up creating redundant representations in the simpler areas, while not being flexible enough to handle the more complex ones. As a result, such methods often suffer from inefficient computation, reduced vectorization accuracy, and limited support for downstream editing tasks. Inspired by this observation, we propose to explore whether the efficiency, accuracy, and editability of image vectorization can be simultaneously achieved when given an input raster image. In contrast, our approach introduces adaptive parameterization, where both the number of paths and the control points on each path are dynamically adjusted based on the complexity of the image. This enables more compact and accurate representations for simple regions and richer, more detailed vectorization for complex ones, striking an effective balance between computational efficiency and flexible editability. For now, let's focus on our approach. Our approach contains three main stages: multi-layer decomposition, control point simplification, and differentiable rendering. First, we break down the input raster image into different layers using semantic segmentation and superpixel clustering. Then, for each layer, we simplify the control points of the vector paths to cut down on redundancy and make sure the paths don't cross over each other. Finally, differentiable rendering is employed to iteratively refine the shape and color parameters of the vectorized layers, ensuring high fidelity to the original image while maintaining vector graphic scalability and editability. Below, we detail each stage of our method. In the multi-layer decomposition stage, we combine semantic segmentation with superpixel partition to generate and filter masks, ensuring semanticity and detail retention in vector graphics. Masks from SAM are prioritized when they have high IOU with superpixel-based masks. The filtered mask set effectively captures the image's human perception hierarchy, with each mask assigned an initial color. In the control point simplification stage, to address redundancy in control points generated by traditional vectorization algorithms, we use Tracer to trace paths and propose an adaptive simplification strategy. We check adjacent Beer curves to identify and remove redundant control points without significantly affecting the path. The simplified path is optimized independently to maintain proximity to the original path while minimizing computational overhead using the chamfer distance loss. In differentiable rendering stage, we use a differentiable renderer to optimize control point and color parameters, minimizing the discrepancy between the rendered image and the input raster image using MSE as the reconstruction loss. A geometric loss is also employed to prevent intersections by penalizing intersection points and undesirable configurations of control points. Now let's look at some experiments and results. We conducted quantitative comparisons between our method and benchmark approaches. The experiments reveal that our method attains superior image reconstruction quality while utilizing fewer paths and parameters compared to the benchmarks, even when those methods employ more resources. Moreover, our method demonstrates a notable speed advantage in generation time. The results show that our method is efficient and effective in image reconstruction tasks. From the qualitative results, we can see that when comparing our proposed method with others in vector graphic reconstruction, the use of a fixed path number in compared methods shows drawbacks. For simple graphics, it causes redundancy, while for complex ones, details are lost. In contrast, our method dynamically adjusts the path number according to image complexity, preserving details and reconstructing various images with high quality using the fewest possible paths. We further demonstrate the applicability of our method to image editing. Leveraging the layer decomposition from vector reconstruction, it enables efficient editing. It can handle delicate gradient color processing for complex contour images and offers flexible applications like color adjustment, object animation, and icon customization. In summary, we introduce an efficient image vectorization approach that guarantees speed, accuracy, and editability. This method dynamically adjusts paths and control points according to image complexity. Benchmark evaluations demonstrate its superior vectorization performance and advantages for image editing tasks. Please see our paper for more details. Thank you all for listening.